I can't hear you guys. See. Can someone try to speak up, please? Are you
Hello,
guys speaking? Iman, try cakap sikit, Iman.
boleh ada. Dengar ada.
Sikit lagi, sikit lagi.
Hello.
Okay. All right. All right. Now that we get things in place, let's start. Um, Two, three. Okay, if you guys check out the lab sheet, please open up the lab sheet. If you guys read. Okay, so this is the our lab sheet. No, this is your mini project part 1B. So in this part of the project, what you guys will learn is we want to implement the scheduling algorithm. Okay, in part 1A, you learn how to create a multi-process, which basically all process do something else. I mean, do things different things, each of the process. And now we want to learn how to schedule our tasks. If you read the lab sheet, it says we had to implement the static scheduler, which is the first scheduler that you learn in lecture. Okay, given in the table. In fact, this table is the same table that we discussed in lecture, okay, of the following set of tasks. And it is the same set of tasks. Okay, basically we have 4 tasks, task 1, 2, 3, and 4. Okay, if you remember in class, we already calculated their hyper period to be 20. Okay, and we are assuming the time units are in seconds. So 4 is 4 seconds, 1 is 1 second, 1.8 is 1.8 seconds, where the hyper period is 20 seconds. Now, you must use fork and exact family of system call to create your task. Okay, you may leave your task to do some dummy calculation as you have done in your lab 1A. Okay, so you can use the same mathematics that you guys have implemented in your task. But if I remember correctly, in 1A, you implement 5 tasks. So here we only need 4, and the timing of the task has to be changed according to the one given here. All right, but our focus in this lab is to implement the scheduler. Now, if you remember from the first lecture we had in the course, right? One moment, I need something to scratch on. Okay. All right, if you remember in class when we talked about, you guys are seeing my screen, right? The
Yes.
lab sheet is being displayed. Yeah. So when we talk about real-time system in general, right, we say I mean, why do we care about scheduling them? Why do we need a scheduler? Okay, to meet all these timing requirements, which is deadline specifically. In your embedded system class, you guys has already learned about interrupt. Okay, interrupt is pretty fast, right? So can't I simply use interrupt to get all these timing requirements done? Like in this case, I have 4 tasks. Period is 4, so deadline is also 4 for task number 1. Second one, period is 5, deadline is also 5. Third one, period is 20, and fourth one also period is 20, which their deadline is also 20. Can I use interrupt? Any answer? To meet the deadline? Can or cannot? Interrupt is meant for what? Ah. Well, the answer generally, yes, we can also use interrupt, okay, under some case, but it doesn't work in all case. Okay, I mean, it depends on the logic, on the number of process, on how the period. So it is not a solution that works for all. Okay, however, let me give I think I already give the example to you guys. If I have 2 tasks, right, like this, task A and task B, this is their period, this is the execution time. This guy 10 period, this guy period is 50. This guy execution time is 2, and this guy execution time is 10. Right, these are tasks. Now the question arises, having these 2 tasks in my system, can I execute them without any problem. I mean that both of them will run meeting their deadline. So of course this is P, so it's also equal to their D. So in the first lecture, what we did was I showed to you guys what is the utilization here. We can calculate them. So this guy is 2 out of 10. This is 10 out of 50, right? So what's the value here? This is equal to 0.2. Here is also 0.2, which means if we total up the total utilization, which is only 0.4, which means our CPU is only busy 40% of the time. 60% of the time, our CPU is free. So looking at this particular fact, can I conclude that both of these tasks can run without missing their deadline? Yes or no? I didn't answer from you guys. Takkan dah lupa kot. Can I execute both tasks without missing their deadline?
Yes,
What makes you say yes?
it's 40% utilization.
Only 40% utilization. 60% of the time the CPU is free. So yeah, we tend to say that. But by right, that is not this information. We cannot conclude schedulability of a set of tasks simply based on utilization. Okay, the answer does not rely on utilization alone. Saying that, what I mean is, if the total U is greater than 1.0, then yes, it's obvious that we cannot schedule. Which means the utilization is more than 100%. I mean, we are talking about uniprocessor, okay? Meaning it needs more than 100% of the time to schedule all tasks. Definitely we cannot do it. However, when the U value is less than 1.0, we cannot also conclude that, yes, we can schedule. There are other things that we have to look at. Look at, right? When U value is less than 1.0, then we cannot conclude that, yes, we can schedule. Okay, let's go deeper into this. The answer relies in, now let's say this is my timeline. All right, this is my timeline. Okay, now I will show you the case where, yes, they will meet their deadline. So this is 0. All right, so what I'll do next is I execute task A first. So it runs for 2 units of time. Okay, the deadline is 10. So yes, it haven't missed its deadline. So after task A is running, next I run task B. Sorry, this typing thing. It's in A. Okay, next I run task B. It runs up to 12. Okay, so B runs for 10 units of time, and the deadline is 50. Well, it's okay, right? And then, of course, can I run task A, the second job of task A again? The answer is yes. Because the second job of task A will be released at time equal to 10. So now time is already 12. So the second job of task A is already there inside the ready state. So I run A. And after that, should I run task B? Well, task B is not there yet. So no problem, I can wait. And then after time is equal to 20, then I can run A once again. If the run time equal to 30, I can run A once again. 40, I can run A once again, right? Once time equal to 50, okay, A is there, B is also there. So I can run A again, and then after that run B. So we don't have any problem with this sequence of execution. So what we are doing here now, we are scheduling them in a way that all of them meets their deadline. Okay. Now, this is the good scheduling. All right. Now let us go into. Kenapa dia ni bergerak-gerak? Aish. Okay lah, saya tak payah padam. Okay, this is the bad one. Okay. Now, if I change the order of execution, I say, let me execute task B first. B run from 0 to 10. After B runs, and I want to run task A, the first job of task A, only 2 units. If I do this, so what happened? By time equal to 10, task A already missed its deadline. See or not? So how do we conclude? The things that I want to highlight here about the importance of scheduling, how you put your task in order, also determines whether or not they meet their deadline, not only the utilization. Okay? That's why if you open the textbook for this course, there are a lot of scheduling algorithms. Now, this is a very simple case. You only have 2 tasks, and their value are very nice, right? 10 and 20 utilization is only 40%. So even at utilization equal to 40%, if you fail to schedule your task correctly, then your task will miss the deadline. So that now what we have to learn, that's why we are learning all this scheduling algorithm, how to make sure that our jobs run without missing the deadline. Because missing deadlines means something bad will happen in real-time system. So that is very, very severe, and we cannot tolerate that. Okay, any question before we proceed? Can you guys understand what I'm trying to highlight here? This is a very important point that you need to understand. If people ask you to explain what is real-time system, why do we care about scheduling? Don't we have interrupt, and that can cater any urgency jobs which are very urgent that can be handled? Yes, interrupt can handle that. Okay, but we cannot guarantee meeting deadline solely with interrupt in the general case. All right. Having that understanding in mind, so let us proceed with our mini project part B. Saya malas nak padam ni. Let me. I saw there's only 90 people here. Almost 1/3 of the class is not here. That is very bad. Okay, I'll save this picture for later. I'll send to go. So let me just close this one here, leave. Then let me share again. Reopen my. All right, now we have a clean sheet. Let me share my screen. Oops, sorry, I shared the wrong screen. Underneath. Okay, back to our discussion on this one. Now, if you look at this one, right, the sequence that we have for this static scheduler is the same sequence that we discussed in class the other day when we talked about static scheduler. So all these 4 tasks, you see this guy is arranged at time 0. Look for T1, okay? So here is T1, here is T1, here is T1, here is T1, here is T1. Now, do you see that they are not periodic? Yes, they are not periodic, right? The way we arrange them, they are not periodic. Basically, the gap from here to here is what? This is 4. What about here to here? It's 4.8. Is it? Yeah. And then from here to here is 9.8, then 13.8, then is again 4. Then from here to here, 13.8. Oh, this is, how come there are 217 here? Is this 16 by right? Let me check our notes. Let me see, yeah. Sekejap. There's a typo there. One lecture notes, PDF, scheduling, static scheduling. Yeah, so T1 was scheduled at time equal to 16. Yeah, correct. Then idle at time equal to 18. Then we have another one. Okay. So at k equal to 13 here, the T sub k, which is the time where T1 is scheduled, the last T1s in the sequence is time equal to 16. Okay, take note on that. Please correct that in your lab sheet as well. And then here is idle, and then T2, and then idle again. Okay. Now, looking at this, what we learned so far is to execute our task periodically. Okay, in mini project 1A. Okay, you're given the period of task A, B, C, D, E. But here the case is different. You only have, you need to execute them in different sequence. So if I set T1, the period is 4, as in theory here. This is the theory. But in the actual case, we schedule them not based on their exact, I mean, at the time the period ends, or the, okay, we arrange them differently. So how do I implement this in implementation? Okay, same goes. In theory here, it says that the period is 5. I mean, that time is equal to 5. I didn't execute them immediately. Now let's check for T2. What about the period of T2? T2 is here, right? And then there's a here, here, and here. So from here to here is what? This is 2, this is 8. So it's 6, right? And then from here to 8, this is 12. That's a 4. And then T2, 12, this is 18, and again 6. Okay, T3 and T4. T3, there's only one T3 in the sequence of 20 because the period is and then T4 is here. All right, so T4, okay, the period is 20. Yeah, we can implement them easily. T4 and T3. So how do we go about implementing T1 and T2? Any idea? Fikirkanlah. Any idea? How do we execute our T1? In the mini project 1A, your task A, you set the period to be what? 3. So every 3 seconds, task A is executed. Not executed, it was released and go inside the ready state. But then when it gets executed, well, we leave it to the scheduler at that point. We haven't touched scheduling in mini project 1A. Kita cuma create the job at every 3 seconds. Meaning, in mini project 1A, what you did was, this is 1A, right? So if this is your ready state, for task A, so every 3 seconds, a new job of task A comes inside your ready state. So every task B berapa? 6 second Dia tak ingat lah. Okay. Task B pula, you send it into every 6 seconds. Task C pula, every 9 seconds. And then task D pula, every 12 seconds. Let's say lah, okay. And then task E every 15 seconds. They gets into the ready state, tapi 3, 3. And then at time was equal to 6, there will be second job of task A. Also, it overlaps with first job of task B. Definitely, there'll have to be scheduling by the OS who runs next. But we don't talk about that in mini project 1A. We simply learn how to create the tasks. So now we slowly go into how do I schedule my tasks? Before this, you leave it to the operating system to schedule them. By right here, we also have a schedule. We are simply looking in implementation. How can we do it? Any idea, anyone? Yes? Anyone wants to try? Kau ni idea ni. Banyak orang suka transcribing ni. Ni kita bincang je. Yes. Any idea how to do it? If you have idea, speak up. There can be more than one solution to it. Maybe you have an idea that I never think of. Yeah. All right. When you write your code, right? when you write your code. For example, for task, whatever it was, main, okay, and then you do some, maybe you create some, let's say your task is task Laplace nowadays. Laplace transform. Kan? So inside here, you pun buat apa loop every 3 seconds. And inside the loop, you panggil your T Laplace. That's what you did, right? For maybe mini project 1A, generally the skeleton is like that. Now, here I have 4 tasks, period 4, 5, 20, and 20. But as we see, the one with period 4 does not get executed at every 4 seconds. The pattern is this one goes at time 0, the next one goes at time 4, right? So how do we go about doing it? I'm restating my question. You see, T1, this guy gets executed at time equal to 0. And of course, after time equal to 20, this whole sequence gets repeated. So every 20 seconds, the same pattern of execution of this set of tasks will get repeated. Okay, nak juga dengar idea kamu ni. So how can we do it? Main thing is I want to get this sequence of execution. Kan? Bagilah sikit pandangan. Ush, tak ada idea ni. Diam je ni. Hello, hello. Takkan dalam ramai-ramai seorang pun tak ada idea. Ada 103 orang ni. Buat macam mana? Jadi engineer ni. Basically, how do I get this? I want that pattern of execution of my task. Baik, let's look into this, right? Mari saya tulis bagi comel sikit. Tulisan ni tak cantik kan? Now, here the period is, before that, let me revise. T is defined by right apa? The 4 tuples, right? Here we only have 2. Now, for T1, the first job of T1 is executed at time equal to 0, period dia 4, execution time dia 1, relative deadline dia 4. Right? Now, the second job of T1, ni kita panggil job number 1 of task number 1. And then job number 2 of task number 1 is executed at time equal to what? 4. Tapi saya tak boleh tulis 4 dekat sini because phase is what? The release time of the first job of a particular task. Okay? Salah kalau saya tulis 4, 4, 1, 4. It's wrong. Okay? Notation wise is wrong. Tapi tak apalah, I want to highlight the idea to you guys. What we can do is I can treat the second job of task T1 as a new task. Okay? So I treat this one not as second job of T1, but as a new task. What I will do is, I say ini T1. But this one is T2. Saya tukar. Tak nak T2 lah. T2 kita dah ada. T3 and T4. So the second job of T1, I treat it as T5. But the alpha is what? Is 4. Period is also 4. Okay. Execution time is 1. How do I make sure that it always get executed here? Right now it's like this, kita katakan. But this, I need to change this. What I'll do is I take the hyper period because what I want is now it's executing here. Once it reach here, the hyper period, I want it to repeat, and again in the second cycle it gets executed at the same spot. So I change the period from 4 to 20. The same goes with T1 here. I change the period to 20. So this guy gets executed at time 0. And then in the second cycle, it also gets executed at time 0. And so deadline dia pun akan berubah jadi 20. Same goes here. And then what about the third job of T1? I treat it as a separate task, T6, which equals to 9.8 here. This is the face value. Okay. Dia punya period pun 20. And then execution time pun sama. And then the fourth job will be T7, which equals to 1, 2, 3, 4, 5 of T1, is it? Yeah. 13.8, 20, 1, and 20. So I'm using the hyper period. So basically in one complete hyper period, all tasks only executed once. Tapi coding wise, of course, you have to make T1, T5, T6, T7, all use the same what? Same code, meaning the same mathematics, same math. And then if T1 do Laplace transform, T5 also Laplace of the same exact code. Nah? And then you get them running in the same pattern. This is workaround. Lah kita kata. What are other ways of doing it? Any other way? This is one way. So here is 16, 20, 1, 20. Okay. Understanding. Same goes with your T2. Lah. You have to split like that. But T2 pun ada how many? 1, 2, 3, 4 of T2. Yeah. So instead of looping every 4 seconds, you loop every 20 seconds for T1, T5, T6, T7, and T8. So now all your tasks will be the same period, which is 20. Yes, you play around with the alpha value, which is the release time of the first job of a task, and everything will follow after that. Any question? Korang ni ada ke tak ada ni? Macam hilang dari wujud je ni. Hello, hello.
Ada.
Dia tak bunyi apa pun. Apa pun tak ada. Any komentar? Any other way of doing it to get the same pattern? Now, what about the execution time? How do you make sure that your task actually execute 1 second? The execution time too refers to what? Oops. Oh, dia berkelip-kelip ni. Memory tak cukup ke apa? It's becoming too heavy. I mean, already. So in my system, it reboot. Oh, sorry. My stylus mengganggu ketenteraman awam. Macam mana adik-adik dan kawan-kawan sekalian? Can follow or not? Well, there are other ways of doing it. So be creative. Nanti saya nak tengok how you guys do it. So here below is a C file. Saya bagi some hint. Number of processes that you need. For each task, you will need a separate C file with executable will pass through the exact C file. Some functions that you may want to use: sleep, micro sleep, nano sleep. This is to create the period ke execution time. In 1A, you use sleep for what? For period or for execution time? Guys, in mini project 1A, for period, right? Now, what about the execution time of your task? You never bother, right? You buat aja. For example, your Laplace transform. How do you know how long it takes to execute? You never measure, but here the time is given to you is 1 second, 1.8. I mean, in 1A pun we give the value, but we didn't bother about that. So how do I make sure that my execution time is as being mentioned here? Basically, you need to make sure that your task 1 execute for 1 second. Nothing more than that. Because if you go beyond, then of course the next job will come slightly later after that. So how do you play around with the logic? You can use some timing function also to measure. And let's say you do your Laplace transform though, you get 0.2 second, your Laplace transform is done. So you need to do that 5 times to get 1 second for the sake of this task. Of course, in the real world, it's not like that again, because basically we do the task first and then we measure how long it takes. That will be the execution time of your task. But here, for the sake of learning, the value is given to you first. So you have to tailor your code to meet the value given. But in the real world, we don't do that. Again, you write your code, then you measure how long it takes. Okay? I'll be continuing online. So you guys can start doing your work for mini project 1B. And if you guys have any questions, then you can ask me. We will stay online until 9:30 for the next half an hour. Okay? Any question you can ask, eh?